Pentium IV is a line of single-core desktop and laptop central processing units introduced by Intel on November 20, 2000 and shipped through August 8, 2008. They had a 7th-generation x86 microarchitecture, called NetBurst, which was the company's first all-new design since the introduction of the P6 microarchitecture of the Pentium Pro CPUs in 1995. NetBurst differed from P6 by featuring a very deep instruction pipeline to achieve very high clock speeds. Intel claimed that NetBurst would allow clock speeds of up to 10 GHz. However, severe problems with heat dissipation limited CPU clock speeds to a much lower 3.8 GHz. In 2004, the initial 32-bit x86 instruction set of the Pentium IV microprocessors was extended by the 64-bit x86-64 set. The first Pentium IV cores, codenamed Willamette, were clocked from 1.3 GHz to 2 GHz. They were released on November 20, 2000, using the Socket 423 system. Notable with the introduction of the Pentium IV was the 400 MTS FSB. It actually operated at 100 MHz, but the FSB was quad-pumped, meaning that the maximum transfer rate was 4 times the base clock of the bus, so it was marketed to run at 400 MHz. The AMD Athlon's double-pumped FSB was running at 100 or 133 MHz at that time. Pentium IV CPUs introduced the SSE2 and, in the Prescott-based Pentium IVs, SSE3 instruction sets to accelerate calculations, transactions, media processing, 3D graphics, and games. Later versions featured hyper-threading technology, a feature to make one physical CPU work as 2 logical CPUs. Intel also marketed a version of their low-end Celeron processors based on the NetBurst microarchitecture, and a high-end derivative, Xeon, intended for multi-processor servers and workstations. In 2005, the Pentium IV was complemented by the Pentium D and Pentium Extreme Edition dual-core CPUs. Microarchitecture: in benchmark evaluations, the advantages of the NetBurst microarchitecture were unclear. With carefully optimized application code, the first Pentium IVs outperformed Intel's fastest Pentium III, as expected. But in legacy applications with many branching or x87 floating-point instructions, the Pentium IV would merely match or run more slowly than its predecessor. Its main handicap was a shared unidirectional bus. Furthermore, the NetBurst microarchitecture consumed more power and emitted more heat than any previous Intel or AMD microarchitectures. As a result, the Pentium IV's introduction was met with mixed reviews. Developers disliked the Pentium IV, as it posed a new set of code optimization rules. For example, in mathematical applications, AMD's lower-clocked Athlon easily outperformed the Pentium IV, which would only catch up if software was recompiled with SSE2 support. Tom Yeager of InfoWorld magazine called it the fastest CPU, for programs that fit entirely in cache. Computer-savvy buyers avoided Pentium IV PCs due to their price premium, questionable benefit, and initial restriction to rambus RAM. In terms of product marketing, the Pentium IV's singular emphasis on clock frequency made it a marketer's dream. The result of this was that the NetBurst microarchitecture was often referred to as a marketecture by various computing websites and publications during the life of the Pentium IV. It was also called NetBust, a term popular with reviewers who reflected negatively upon the processor's performance. The two classical metrics of CPU performance are IPC and clock speed. While IPC is difficult to quantify due to dependence on the benchmark application's instruction mix, clock speed is a simple measurement yielding a single absolute number. Unsophisticated buyers would simply consider the processor with the highest clock speed to be the best product, and the Pentium IV had the fastest clock speed. Because AMD's processors had slower clock speeds, it countered Intel's marketing advantage with the Megahertz Myth campaign. AMD product marketing used a peer rating system, which assigned a merit value based on relative performance to a baseline machine. At the launch of the Pentium IV, Intel stated that NetBurst-based processors were expected to scale to 10 GHz after several fabrication process generations. However, the clock speed of processors using the NetBurst microarchitecture reached a maximum of 3.8 GHz. Intel had not anticipated a rapid upward scaling of transistor power leakage that began to occur as the die reached the 90 nm lithography and smaller. This new power leakage phenomenon, along with the standard thermal output, created cooling and clock scaling problems as clock speeds increased. Reacting to these unexpected obstacles, Intel attempted several core redesigns and explored new manufacturing technologies, such as using multiple cores, increasing FSB speeds, increasing the cache size, and using a longer instruction pipeline along with higher clock speeds. These solutions failed, and from 2003 to 2005, Intel shifted development away from NetBurst to focus on the cooler-running Pentium M microarchitecture. On January 5, 2006, Intel launched the Core processors, which put greater emphasis on energy efficiency and performance per clock cycle. The final NetBurst-derived products were released in 2007, with all subsequent product families switching exclusively to the Core microarchitecture. Processor cores. Pentium IV processors have an integrated heat spreader that prevents the die from accidentally being damaged when mounting and unmounting cooling solutions. Prior to the IHS, a CPU shim was sometimes used by people worried about damaging the core. Overclock has sometimes removed the IHS from socket 423 and socket 478 chips to allow for more direct heat transfer. On processors using the socket LGA 775 interface, the IHS is directly soldered to the die or dies, making it difficult to remove. Willamette. Willamette, the project codename for the first NetBurst microarchitecture implementation, experienced long delays in the completion of its design process. The project was started in 1998, when Intel saw the Pentium II as their permanent line. At that time, the Willamette core was expected to operate at frequencies up to about 1 GHz. However, the Pentium III was released while Willamette was still being finished. Due to the radical differences between the P6 and NetBurst microarchitectures, Intel could not market Willamette as a Pentium III, so it was marketed as the Pentium IV. On November 20, 2000, Intel released the Willamette-based Pentium IV clocked at 1.4 and 1.5 GHz. Most industry experts regarded the initial release as a stopgap product, introduced before it was truly ready. According to these experts, the Pentium IV was released because the competing Thunderbird-based AMD Athlon was outperforming the aging Pentium III, and further improvements to the Pentium III were not yet possible. This Pentium IV was produced using a 180 nm process and initially used socket 423. With later revisions moving to socket 478. These variants were identified by the Intel product codes 80528 and 80531 respectively. On the test bench, the Willamette was somewhat disappointing to analysts in that not only was it unable to outperform the Athlon in the highest clocked Pentium IIIs in all testing situations, but it was not superior to the budget segment's AMD Duran. Although introduced at prices of $644 and $819 for 1,000 quantities to OEM PC manufacturers, it sold at a modest but respectable rate, handicapped somewhat by the requirement for relatively fast yet expensive RAM-based dynamic RAM. The Pentium III remained Intel's top-selling processor line, with the Athlon also selling slightly better than the Pentium IV. While Intel bundled two DRAM modules with each boxed Pentium IV, it did not facilitate Pentium IV sales and was not considered a true solution by many. In January 2001, a still slower 1.3 GHz model was added to the range, but over the next 12 months, Intel gradually started reducing AMD's leadership in performance. In April 2001 a 1.7 GHz Pentium IV was launched, the first model to provide performance clearly superior to the old Pentium III. July saw 1.6 and 1.8 GHz models, and in August 2001, Intel released 1.9 and 2 GHz Pentium IVs. In the same month, They released the 845 chipset that supported much cheaper PC133 SDRAM instead of a DRAM. The fact that SDRAM was so much cheaper caused the Pentium IV's sales to grow considerably. The new chipset allowed the Pentium IV to quickly replace the Pentium III, becoming the top-selling mainstream processor on the market. The Willamette codename is derived from the Willamette Valley region of Oregon, where a large number of Intel's manufacturing facilities are located. Northwood. In January 2002, Intel released Pentium IVs with a new core codenamed Northwood at speeds of 1.6 GHz, 1.8 GHz, 2 GHz and 2.2 GHz. Northwood combined an increase in the L2 cache size from 256 KB to 512 KB with a transition to a new 130 nm fabrication process. Making the processor out of smaller transistors means that it can run at higher clock speeds and produce less heat. In the same month, boards utilizing the 845 chipset were released with enabled support for DDR-SDRAM, which provided double the bandwidth of PC133 SDRAM, and alleviated the associated high costs of using Rambus RDRAM for maximal performance with Pentium IV. A 2.4 GHz Pentium IV was released on April 2, 2002, and the bus speed increased from 400 MTS to 533 MTS for the 2.26 GHz, 2.4 GHz, and 2.53 GHz models in May, 2.66 GHz and 2.8 GHz models in August, and 3.06 GHz model in November. With Northwood, the Pentium IV came of age. The battle for performance leadership remained competitive, but most observers agreed that the fastest clocked Northwood-based Pentium IV was usually ahead of its rival. This was particularly so in mid-2002, when AMD's changeover to its 130 nm production process did not help the initial thoroughbred revision Athlon XP CPUs to clock high enough to overcome the advantages of Northwood in the 2.4 to 2.8 GHz range. The 3.06 GHz Pentium IV enabled hyper-threading technology that was first supported in Foster-based Xeons. This began the convention of virtual processors under x86 by enabling multiple threads to be run at the same time on the same physical processor. By shuffling two program instructions to simultaneously execute through a single physical processor core, the goal is to best utilize processor resources that would have otherwise been unused from the traditional approach of having these single instructions wait for each other to execute singularly through the core. This initial 3.06 GHz 533 FSB Pentium IV hyper-threading-enabled processor was known as Pentium IV HT and was introduced to mass market by Gateway in November 2002. On April 14, 2003, Intel officially launched the new Pentium IV HT processor. This processor used an 800 MTS FSB, was clocked at 3 GHz, and had hyper-threading technology. This was meant to help the Pentium IV better compete with AMD's Opteron line of processors. The server-oriented Opteron initially did not share a common socket with AMD's desktop processor line. Because of this, motherboard manufacturers did not initially build motherboards with AGP for Opterons. As AGP was the primary graphics expansion port for desktop use, this oversight prevented the Opteron from encroaching from the server market and threatening the Pentium IV desktop market. Meanwhile, with the launch of the Athlon XP 3200 Plus in AMD's desktop line, AMD increased the Athlon XP's FSB speed from 333 MTS to 400 MTS, but it was not enough to hold off the new 3 GHz Pentium IV HT. The Pentium IV HT's increase to a 200 MHz quad-pumped bus greatly helped to satisfy the bandwidth requirements the NetBurst architecture desired for reaching optimal performance. While the Athlon XP architecture was less dependent on bandwidth, the bandwidth numbers reached by Intel were well out of range for the Athlon's EV6 bus. Hypothetically, EV6 could have achieved the same bandwidth numbers, but only at speeds unreachable at the time. Intel's higher bandwidth proved useful in benchmarks for streaming operations, and Intel marketing wisely capitalized on this as a tangible improvement over AMD's desktop processors. Northwood 2.4 a GHz, 2.6 a GHz and 2.8 a GHz variants were released on May 21, 2003. A 3.2 a GHz variant was launched on June 23, 2003 and the final 3.4 a GHz version arrived on February 2, 2004. Overclocking early stepping Northwood cores yielded a startling phenomenon. While core voltage approaching 1.7 V and above would often allow substantial additional gains in overclocking headroom, the processor would slowly become more unstable over time with a degradation in maximum stable clock speed before dying and becoming totally unusable. This became known as sudden Northwood death syndrome, which is caused by electromigration. Pentium IVM, also based on the Northwood core, the mobile Intel Pentium IV processor, was released on April 23, 2002 and included Intel's speed step and deeper sleep technologies. Intel's naming conventions made it difficult at the time of the processor's release to identify the processor model. There was the Pentium III mobile chip, the mobile Pentium IVM, the mobile Pentium IV, and then just the Pentium M, which itself was based on the Pentium III and significantly faster than the former three. Its TDP is about 35 watts in most applications. This lowered power consumption was due to lowered core voltage, and other features mentioned previously. Unlike the desktop Pentium IV, the Pentium IVM did not feature an integrated heat spreader, since it operates at a lower voltage. The lower voltage means lower power consumption, and in turn less heat. However, according to Intel's specifications, the Pentium IVM had a maximum thermal junction temperature rating of 100 degrees Celsius, approximately 40 degrees higher than the desktop Pentium IV. Mobile Pentium IV, the mobile Intel Pentium IV processor was released to address the problem of putting a full desktop Pentium IV processor into a laptop, which some manufacturers were doing. The mobile Pentium IV used a 533 LMTS FSB, following the desktop Pentium IV's evolution. Oddly, increasing the bus speed by 133 LMTS caused a massive increase in TDPs, as mobile Pentium IV processors emitted 59.8 W, 70 W of heat, with the hyper-threading variants emitting 66.1 W, 88 W. This allowed the mobile Pentium IV to bridge the gap between the desktop Pentium IV and the Pentium IVM. Gallatin, in September 2003, at the Intel Developer Forum, the Pentium IV Extreme Edition was announced, just over a week before the launch of Athlon 64 and Athlon 64FX. The design was mostly identical to Pentium IV, but differed by an added 2 MB of Level 3 cache. It shared the same Gallatin core as the Xeon MP, though in a socket 478 form factor and with an 800 MTS bus, twice as fast as that of the Xeon MP. While Intel maintained that the Extreme Edition was aimed at gamers, critics viewed it as an attempt to steal the Athlon 64's launch thunder, nicknaming it the Emergency Edition. With a price tag of $999, it was also referred to as the Expensive Edition, or extremely expensive. The added cache generally resulted in a noticeable performance increase in most processor-intensive applications. Multimedia encoding and certain games benefited the most, with the Extreme Edition outperforming the Pentium IV, and even the two Athlon 64 variants, although the lower price and more balanced performance of the Athlon 64 led to it usually being seen as the better value proposition. Nonetheless, the Extreme Edition did achieve Intel's apparent aim, which was to prevent AMD from being the performance champion with the new Athlon 64, which was winning every single major benchmark over the existing Pentium IVs. In January 2004 a 3.4 GHz version was released for socket 478, and in summer 2004 the CPU was released using the new socket 775. A slight performance increase was achieved in late 2004 by increasing the bus speed from 800 MTS to 1066 MTS, resulting in a 3.46 GHz Pentium IV Extreme Edition. By most metrics, this was on a per-clock basis the fastest single-core NetBurst processor that was ever produced, even outperforming many of its successor chips. Afterwards, the Pentium IV Extreme Edition was migrated to the Prescott core. The new 3.73 GHz Extreme Edition had the same features as a 6x0 sequence Prescott 2M, but with a 1066 EMTS bus. In practice, however, the 3.73 GHz Pentium IV Extreme Edition almost always proved to be slower than the 3.46 GHz Pentium IV Extreme Edition, which is most likely due to the lack of an L3 cache and the longer instruction pipeline. The only advantage the 3.73 GHz Pentium IV Extreme Edition had over the 3.46 GHz Pentium IV Extreme Edition was the ability to run 64-bit applications, since all Gallatin-based Pentium IV Extreme Edition processors lacked the Intel 64 instruction set. Although never a particularly good seller, especially since it was released in a time when AMD were asserting near-total dominance in the processor performance race, the Pentium IV Extreme Edition established a new position within Intel's product line, that of an enthusiast-oriented chip with the highest-end specifications offered by Intel chips, along with unlocked multipliers to allow for easier overclocking. In this role it has since been succeeded by the Pentium Extreme Edition, the Core 2 Extreme, and most recently, the Core i7. Prescott. On February 1, 2004, Intel introduced a new core codenamed Prescott. The core used the 90nm process for the first time, which one analyst described as a major reworking of the Pentium IV's microarchitecture, major enough that I am surprised Intel did not opt to call this processor the Pentium 5. Despite this overhaul, the performance gains were inconsistent. Some programs benefited from Prescott's double cache and SSE3 instructions, whereas others were harmed by its longer pipeline. The Prescott's microarchitecture allowed slightly higher clock speeds, but not nearly as high as Intel had anticipated. The fastest mass-produced Prescott-based Pentium IVs were clocked at 3.8 GHz. While Northwood ultimately achieved clock speeds 70% higher than Willamette, Prescott scaled 12% beyond Northwood. Prescott's inability to achieve greater clock speeds was attributed to the very high power consumption and heat output of the processor. In fact, Prescott's power and heat characteristics were only slightly higher than those of Northwood of the same speed and nearly equal to the Gallatin-based Extreme Editions, but since those processors had already been operating near the limits of what was considered thermally acceptable, this still posed a major issue. The Prescott Pentium IV contains 125 million transistors and has a die area of 112 ohm2. It was fabricated in a 90 nm process with 7 levels of copper interconnect. The process has features such as strained silicon transistors and low-K carbon-doped silicon oxide dielectric, which is also known as organosilicate glass. The Prescott was first fabricated at the D1C development fab and was later moved to F11X production fab. Originally, Intel released 2 Prescott lines, the E-series, with an 800 MTS FSB and hyper-threading support, and the low-end A-series, with a 533 MTS FSB and hyper-threading disabled. Intel eventually added XD-bit and Intel 64 functionality to Prescott. LGA 775 Prescott uses a rating system, labeling them as the 5XX series. The LGA 775 version of the E-series uses model numbers 5X0, and the LGA 775 version of the A-series uses model numbers 5X5 and 5X9. The fastest, the 570J and 571, is clocked at 3.8 GHz. Plans to mass-produce a 4 GHz Pentium IV were cancelled by Intel in favor of dual-core processors, although some European retailers claim to be selling a Pentium IV 580, clocked at 4 GHz. The 5XOJ series introduced the XD bit aka Execute Disabled bit to Intel's line of processors. This technology, introduced to the x86 line by AMD and called NX, can help prevent certain types of malicious code from exploiting a buffer overflow to get executed. Intel also released a series of Prescott supporting Intel 64, Intel's implementation of the AMD-developed x86-64 64-bit extensions to the x86 architecture. These were originally released as the F-Series, and only sold to OEMs, but they were later renamed to the 5X1 series and sold to the general public. Two low-end Intel 64-enabled Prescotts, based on the 5x5/5x9 series, were also released with model numbers 506 and 516. 5XO, 5XOJ, and 5X1 series Prescott incorporates hyper-threading in order to speed up some processes that use multi-threaded software, such as video editing. The 5X1 series also supports 64-bit computing. Prescott 2M, Intel, by the first quarter of 2005, released a new Prescott core with 6XO numbering, codenamed Prescott 2M. Prescott 2M is also sometimes known by the name of its Xeon derivative, Irwindale. It features Intel 64, the XD-bit, EIST, TM2, and 2 MB of L2 cache. However, higher cache latency and the double word size, if using Intel 64 mode, negated any advantage that added cache introduced. Rather than being a targeted speed boost, the double-size cache was intended to provide the same space and hence performance for 64-bit mode operations. 6XX series Prescott 2 milliseconds have incorporated hyper-threading in order to speed up some processes that use multi-threaded software, such as video editing. On November 14, 2005, Intel released Prescott 2M processors with VT enabled. Intel only released two models of this Prescott 2M category, 662 and 672, running at 3.6 GHz and 3.8 GHz, respectively. Cedar Mill, the final revision of the Pentium IV was Cedar Mill, released on January 5, 2006. This was a die shrink of the Prescott-based 600 series core to 65 nanometers, with no real feature additions but significantly reduced power consumption. Cedar Mill had a lower heat output than Prescott, with a TDP of 86 W. The core stepping of DO in late 2006 reduced this to 65 watts. It has a 65 nm core and features a 31-stage pipeline, 800 MTSFSB, Intel 64, hyper-threading, but no virtualization technology. As with Prescott 2M, Cedar Mill also has a 2 MB L2 cache. It was released as Pentium 6X1 and 6X3 at frequencies from 3 GHz up to 3.6 GHz. Overclockers managed to exceed 8 GHz with these processors using liquid nitrogen cooling. To distinguish Cedar Mill cores from Prescott cores with the same features, Intel added one to their model numbers. Thus, Pentium IV 631, 641, 651 and 661 are 65 nm Cedar Mill microprocessors, while Pentium 630, 640, 650 and 660 respectively are their 90 nm Prescott equivalents. The name Cedar Mill refers to Cedar Mill, Oregon, an unincorporated community near Intel's Hillsboro, Oregon facilities. Successor. The original successor to the Pentium IV was Tejas, which was scheduled for an early mid-2005 release. However, it was cancelled a few months after the release of Prescott due to extremely high TDPs and development on the NetBurst microarchitecture as a whole ceased, with the exception of the dual-core Pentium D and Pentium Extreme Edition and the Cedar Mill-based Pentium IV HT. Since May 2005, Intel has released dual-core processors based on the Pentium IV under the names Pentium D and Pentium Extreme Edition. They represent Intel's shift towards parallelism, and their intent was to eventually make the bulk of their main processor line multiple-core. These came under the codenames Smithfield and Pressler for the 90 nm and 65 nm parts respectively. The ultimate successors to Pentium IV are the Intel Core 2 processors using the Conroe core based upon the Core microarchitecture, released on July 27, 2006. Intel Core 2 processors have been released as single, dual and quad-core processors. Single-core counterparts are present in the Intel Core 2 line, primarily for the OEM market, while dual and quad-core processors can be sold to retail and OEM. See also: Notes and references. External links: The Future of Prescott, When More Gives You Lemons. At Ars Technica, Prescott vs. Northwood Pentium IV Review, Intel Documentation, Inside Pentium IV Architecture, the microarchitecture of the Pentium IV processor.